These three questions all deal with adjusting the tonicity of a solution, but if you use the same method for all three, you'll get at least two of them wrong. Now, the hardest part when it comes to calculations involving adjusting the tonicity of a solution is not really the math, it's actually recognizing which method the question is actually testing. So in this video, I'll walk you through three tonicity questions, each using a different method, and show you how to identify the correct approach before you calculate anything. And we are starting right now. Hello, this is Dr. Dankwa, and if this is your first time here and you like to learn pharmaceutical calculations, tips, tricks, and strategies, then start by subscribing and clicking the bell so you don't miss anything. So here the question is presented and it says how many milliliters of purified water should be used in compounding the prescription. Round to the nearest tenth, do not include units. So as a general rule, when you see a question and it's asking for the volume of purified water or the volume of isotonic buffer that is needed, then generally you're going to be using the White-Vincent method equation or the White-Vincent method. And then the equation for that is going to be your V, which is volume, is equal to the weight in grams of the first component times its E value plus, in this case, because we have two components, we're going to do the weight in grams of the second component times its E value, and all of this times 111.1. So here again, the real tell is it asks for the volume in milliliters of purified water. So having said that, what we have here are the percentage concentrations. And so notice that this is the weight in grams. That's for the omegas. So you want to convert the 0.3% to its equivalent in grams. And you always be using the volume of your preparation to accomplish that task. So here we are going to have the 0.3%, which is 0.3 grams in 100 milliliters. And we're going to multiply that by the volume you're making here, which is 60 ml. And as soon as we do that, we are going to end up with the weight in grams. So everything in these parentheses right here, it's for the omega-1. And then we're going to multiply this by its E value. And then the question is 0.18. And you're going to add to that the equivalent for ingredient B. So we're going to do the same thing here. 0.2% is 0.2 grams over 100 milliliters times the volume, which is 60 ml, times its E value, which is 0.15. And all of this times 111.1. That's this factor right here. So when you do the math on your calculator, you're going to end up with something like 0.0324 plus 0.018, all of that times 111.1. And now that's going to be equal to 5.6. And that'll be your answer for that question. So make sure that you can quickly identify if the question is asking for you to use the White-Vincent method. And typically it's going to say the volume of purified water or the volume of your isotonic buffer. So if it's asking for the volume of isotonic buffer, then you're going to subtract this value, which is the 5.6, from your total volume. And in this case, it's going to be 60 ml. And so that would have been 54. But here it's only asking for your volume of purified water. So let me actually just write that down. If it asks for the volume of isotonic buffer, it will be the total volume you're making minus the volume of your purified water. And so you end up with 50. All right, so now in this question, it actually tells you what method to use indirectly. So in the question, it gives you the freezing point depression, and you can basically make that inference that this question is going to be solved using the freezing point depression because you don't really see any other information that may be pertinent to allow you to solve the question. So what you're going to do is you're going to start up with the first step, and in that step, you want to first determine what exactly is the freezing point depression of this particular preparation. And notice that these values that are given are normally for 1% solution. So here, we have a 2% solution. So we're going to take that value, which is 0.07, and we're going to multiply that by 2, and that's going to give us 0.14. So this 0.14 is where this preparation's freezing point depression is at the moment, right? So in step 2, we're going to compare that to what the freezing point depression is for an isotonic solution, and we mentioned that that is 0.52. So we're going to subtract step 1, which is 0.14 from the 0.52. And now that gives us 0.38. What this means is we need to add some amount of salt or boric acid in this instance to get the freezing point depression lowered by an additional 0.38. Now, the way we want to do that is we first are going to do a step 3. And here we are going to make the statement that 0.9% sodium chloride solution has a freezing point depression of 0.52. As we mentioned in class, the 0.9% sodium chloride solution, also known as normal saline, is isotonic, and anything that is isotonic has a freezing point depression of 0.52. So now this is going to be equal to some percentage over the value you get in step 2. So when we solve for x is going to be equal to 0.9% times 0.38 over 0.52, and now that gives 0.658%. But we don't stop here because the question is actually asking for the quantity in grams. And this, as of now, is your percentage concentration of a sodium chloride solution that is needed to get to 0.38 freezing point depression. So we want to take this 0.658 and then express it as 0.658 grams in 100 milliliters. And now we are going to say, what is the quantity in grams that will be needed for the volume that we are making? And here we are making a 45 milliliter preparation. So we solve for the y. Y is going to be equal to 0.658 grams times the 45 divided by 100. And that's going to be equal to 0.2961 grams. And we are in NaCl. But notice the question is asking for boric acid. So what we can do is we can divide this 0.2961 by the E value of the boric acid, which is 0.52, and it will give us 0.56942. And now you're in boric acid. So let's put that here. But we need to be in milligrams. So we do a quick conversion. So 1 gram is 1,000 milligrams. And now you end up with 569.4. It says round to the nearest tenth. So you want to pay attention to that and do not include units. All right. So here the question says how many milliliters of a 0.9% sodium chloride solution should be used in compounding the preparation. So even though it says how many milliliters, it's not asking for purified water. So we're not going to use the white Vincent method here. And also, we do not have any freezing points or freezing point depressions in this question. So we're not going to use the freezing point depression method here. What we are going to do is we're going to use the sodium chloride equivalent method. And to do that, we start off with the first step. And the first step is to determine how many grams or milligrams, but most of the time grams, of sodium chloride will be needed to make a volume of 15 ml isotonic if there was nothing else in it. So we start off with the notion that 0.9%, which is 0.9 grams of sodium chloride in 100 milliliters is isotonic. So what will be its equivalent mass that will be needed to make 15 ml isotonic? So we solve for x. X is going to be equal to 0.9 grams times 15 milliliters divided by 100. And now that's going to be equal to 0.135 grams NaCl. And I'm just going to put that right here. So the next thing we want to do is we want to do the step 2. And in the step 2, we are going to do the contribution from each of these ingredients, from the phenylephrine hydrochloride and then the chlorobutanol. And so the way we do that is we want to get the quantity in grams and multiply by its E value. So anytime you're doing that operation, it's always the amount in grams. And I want to emphasize that because it's a critical thing to recall. You're not going to be using the percentage. You want to get the percentage into the amount in grams. And then when you get that value, you multiply by the E value. All right, so we're going to do it in 2 steps. We're going to start off with the phenylephrine hydrochloride. So what that will mean is we're going to take the 1%, which is 1 gram over 100 milliliters. And we are going to multiply that by the volume we are compounding, which is 15 milliliters. So now we are in grams, and then we can multiply by the E value, which is 0.32 in this instance. So that's going to be equal to 0.048 grams NaCl. So now we're going to do the same thing for the chlorobutanol. And since this is a concentration, it's 0.5 grams in 100 milliliters, but we are compounding a 15 milliliter preparation. So we multiply by 15 milliliters and then we multiply by its E value, which is 0.24. And now what you have is going to be 0.018 grams. And all this is NaCl. And so now in step 3, we're going to subtract the values we got in step 2 from what we had in step 1. Now you can add these 2 values and subtract them, or you can subtract them like sequentially. So we're going to start off with the value from step 1, which is 0.135 grams. And we will subtract the 0.048, which is the contribution from the phenylephrine hydrochloride. And we're going to subtract the value for the chlorobutanol, which is 0.018 grams. Now, when we do all of that, we're going to end up with a value which is 0.069 grams NaCl. Now, having said that, if we're simply going to weigh this out and make the preparation isotonic, then we will stop here. But the way you're going to supply this amount of sodium chloride is to use a stock solution, and actually you're using normal saline, right? So now you need to find the equivalent volume of normal saline, or 0.9% sodium chloride solution, that will give you the 0.069 grams, or essentially 69 milligrams. So we need to do one more step, and what that would look like is it will be a very elegant, quick proportion. So we'll start off with the concentration here of the solution, and it's 0.9 grams in 100 milliliters. And the question is, what is that volume that will be needed to give you 0.069 grams, right? So we are looking for, in the denominator here, some volume. So you do the algebra, and you end up with 7.67. So I hope you found this video tutorial useful. If you did, be sure to like it and share it. And if you have any questions, just leave them in the comments and I'll get to them as soon as I see them. If you'd like to learn more pharmaceutical calculations, tips, tricks, and strategies, then start by subscribing and clicking the bell so you don't miss anything. Thank you so much for watching, and I'll see you in the next video.